Of course. Okay, so basically we have Ben and Owen here, and both of them are, well, Ben's the founder of ArtMatr, and Owen is an engineer and coder. And so today, if you've checked out the Slack and all of that, we have like our place and the little pixel art that people have been editing and putting stuff on and drawing and messing with. But we basically sent a copy of like the art from a few days ago of like everything, all the designs that people put on there before like whatever happened. But they're going to recreate that on like a real IRL canvas with their robots and machines, and do it on Zoom, and we're going to watch them do it and explain it and all of that. And so it's going to be more of a show and tell, not exactly AMA, but you can ask questions and like talk to them. It's going to be really cool.
Epic. Do we feel good to get started, everyone? Owen, Ben, Mark.
Yeah, I think we're just about ready to start. Good to meet you all. Yeah, I'm Owen, and then this is Ben.
Hi, everyone.
Yeah, Ben, maybe Ben, you want to explain what ArtMatr does?
Yeah, so I'll give just a very quick intro into why we're doing what we're doing. And I said to Mark a little bit of the education here, just the reality of startups. We're always doing 12 things at once. So some investors, collectors coming through. But I'll give a little bit of an intro and I'll have to jump out for a bit, but I'll be observing from the background. But anyway, very, very pleased to be talking to you all today. My personal background is as a painter. I started an art school early on when I was much younger in Israel, and I exhibited both in New York and Paris. But there was just this period of a couple of decades of seeing virtually every creative space completely upended by digital tech, with painting probably being the one exception of all the creative disciplines, which left me very frustrated and interested to see how that could transform. And what started off as a passion ended up as a company. But primarily seeing all of the explosion in digital imaging and combined with some of the hardware around tablets, it seemed like there was this amazing possibility to take all of the latent creativity, both the tech and the talent, from the digital space and move it into the physical. So that is, artists were already trying to use printers. Some were obviously using plotters for a while, but they were very limited. And it wasn't because of the core, and the way what I thought was, it wasn't because of the inherent limitations of the technology, but more the way the industry went. It was sort of designed in a way that I felt was anti-creative. It was very limited in terms of your ability to get in and explore and create the happy accidents that often make the best art. So I took my personal background in traditional painting, even like really traditional, like old master copying, that kind of thing that I use as a learning and a teaching methodology, and I tried to apply those same principles to the space. So at the time, I came to MIT to help run some projects. That's how I met Owen, and Owen blew everyone away with his ability to tap into virtually any part of software or hardware, electronics, et cetera, and robotics, and go very, very far and pull all of those things together. And we started prototyping. So Owen was literally building. Oh, it's doing.
Sorry, one second.
This chaos of startups. Anyway, but that was the intro. So Owen, quickly came on board with a few other folks at MIT, and some other academic and corporate partnerships, and we started prototyping, for lack of a better term, painting machines. So we'll show you some of that, some of the machines that are our normal go-to in our labs, and some of the stuff that's actually still being built in the form of an active demo today. And just separately, we're trying to do a lot more outreach on social. So we generally on Wednesday afternoon, we do a live stream, kind of, Q&A. And you can know any sort of questions or follow-up, please reach out to us, and we'd love to continue the conversation in multiple forms.
Yeah, maybe any questions after that intro, just kind of generally, especially about ArtMatr as a whole, or otherwise we can jump into technical stuff maybe. I know hopefully we'll get another camera angle and I can show you some of the machines.
Yeah, I think we'd love to, maybe Owen, you could introduce yourself a little bit just so everyone can know what you do, etc.
Sure. So yeah, Ben and I met at MIT because I was working in the MIT Media Lab for Neri Oxman on the glass 3D printer project that her group was doing there. And I did my undergrad at MIT, but I dropped out after 2.5 years and then did a bunch of product development. So lots of hardware products and of all sorts. Some of them were for artists doing custom engineering for art installations, and then others were things like induction cooktops, robotic therapeutic systems, drug delivery systems, all kinds of marketing activations, all kinds of random stuff. So because of that, I got to work on a lot of different kinds of hardware and software projects. When I was in school, I studied computer science and electrical engineering. And I've ended up, I'm much stronger on the software, but it's been helpful to have the electrical background. And, alluding to the chaos of startups, I've spent most of my time in startups, and I think it's really helpful to have a generalist toolkit. So that's what I've been applying here. In my own research, I'm really excited about human-machine interaction and how creative tools can be built better for people, especially ones that cross the divide between physical and digital space. And I think that's going to be more and more relevant very soon now because of these advancements that are being made in robotics, especially, where it's getting easier to have robots do meaningful things in the real world rather than just kind of, very constrained things in a lab. Cool. So maybe then can jump into technical stuff. You guys feel okay with that? Cool. Is there a question?
Oh, yeah, I just had a question about ArtMatr. What are some use cases you see for this technology? What are some ways it's being put to use?
So we've been doing this for nearly 8 years.
Mm-hmm.
And the way that it's worked is we started off looking at, almost like Venn diagram style. We looked at existing kind of artistic principles, the building blocks for paintings, and looked at them as an overlap with existing or emerging technologies. And my perspective was not to focus on the things where we can get robotics to replace what people do, but look at the things where robotics, all of the tech, can go way beyond what a person could even dream of, and start to kind of drill down there. And that was the principle. It's kind of changed a little bit. Sometimes just getting the robotics to replicate what humans do a little bit better is actually a very interesting thing. But we started prototyping these things based on assumptions, one at a time, and then bringing them out into the field. What do I mean? I felt that in order to make this whole thing take off, we needed to find a common lexicon, like a common language that both creatives and engineers, developers could speak. They might speak English, but they're not really understanding one another, because they share such a different language and way of speaking and just sort of worldview, right? So as soon as we had prototypes where people could see the machine and see how it worked and see what the results could be, then they had something they could literally point to, right? And both artist and engineer could literally just point to it and say, this is good, this is bad, can we do this? What if, that kind of thing. And so we started bringing in, we had this obviously amazing team of engineers from MIT and other places. And then we had some of the world's leading artists actually come up to MIT and start working with us, literally like the most successful, at least in financial terms, artists in the world. People like Chuck Close, who passed away last year, but Jeff Koons, that level, right? People that are selling work for millions of dollars per piece. They would work with us to play around with the tools, give feedback, and produce work. And eventually we got good enough at that, and we started bringing in these people as clients and doing bodies of work and showing them in these big galleries, or just doing bodies of work that they would sell in various ways. And we have a few different types of toolkits that apply to different types of artists. One is the traditional artist that builds up paintings in a sort of retrofits the way that we do things by hand. And more recently is this other group with generative art, which is more interesting because these are people that are obviously starting off with code. And if they're obviously, they either have not made physical things yet, or if they have, they're already working with plotters or printers. So what we're building is just a natural extension of what they're already doing. So it's exciting for me to see people come in, bring in their studio, which is effectively their laptop, plug into our machines and start painting for the first time. And it's like they're never picking up a paintbrush by hand probably, but they're making these fascinating things that's all coming out of their imagination code. So there's a kind of, not just artist engineer, but in digital physical, but there's this other space which is emerging between generative and traditional that's coming into play. So we're exploring that, and we're trying to bring the most benefit to the largest number of people. But the tools that Owen's about to show you are designed for a much wider audience with the plotter farms. So you don't have to be a blue chip artist selling at millions of dollars to use this stuff. You can be a student, younger artist, emerging artist, and come in and take advantage of it.
Wow, that's awesome.
That's amazing. So thank you for answering that. Let's jump in and look at those tools that Owen's going to show us. Go ahead. And guys, so Mark has his phone out and recording at the right now. So that's what's happening on Mark's screen. Owen, go ahead. You and Ben can show.
Sure. Maybe I think Mark's in the other room, but it'd be a good time to bring in that other camera angle. I'll kind of give you a glimpse of this machine, which great. Yeah, just anywhere, just kind of generally. Maybe I'll give a broad review. So this machine that we're looking at is, we're calling it the plotter farm, and it's designed to be kind of like a server rack. If you've ever seen that, you have a big frame and then a whole bunch of individual, in that case, computers, but in this case, plotters. Each one is an XYZ gantry, so it can move a tool in three-dimensional space, and the stack together can do work in parallel. So the direction we're working towards is to put this online. So you could go to a website and prepare some art that you want to submit. For example, the art that you guys sent me, and you'd translate it to a job that one of these machines could run, and then be able to execute it, like ask the system to do the work physically. It would record what it's doing. It has cameras on board, so it can capture video and time lapses and audio as well, of just because it's fun, of the creation of the work, and then it returns that back to you, and you get that before you get the work shipped to you in the mail. And it's kind of related to this hybrid way of working where you are working digitally, like Ben said. Like a lot of digital artists, generative artists are working with us now. By default, they're working in code. They're generating images, but behind that, there's geometry and behaviors and the algorithms they're using. Those can direct these machines, and you'll get a different effect no matter what. Even if you run the same, you run some code and you get an image on the screen. If you run the same code, kind of with the generating the same geometry, but send it to one of these machines, you'll get a different result because of the physical nature of the medium, the tools that you use, the substrate that you pick. that'll all lead to a little variation. And in the end, you can use that artistically, however you want. So eventually, it might be that you use this interactively, you submit work, it executes it, records it, sends it back to you, and you don't actually get it shipped to you immediately. You can just do these tests very quickly. And then when you're happy with the effect that you've gotten, that's when you could submit it as a real job and get it shipped back to you. So with that as the kind of the context for the problem is this particular machine solves, you can kind of understand some of the design decisions. So it's very lightweight and relatively cheaply built. That's so that we can have as many of these individual layers as possible. From like kind of a pipeline perspective, the thing that is the bottleneck is just the production of the work. Each machine, has maybe like one large artwork or several small artworks dedicated to it, but there's only one toolhead. So the toolhead has to share time among whatever artworks are loaded onto the bed. And that really encourages parallelism. So having as many machines in the frame as possible. So eventually we're hoping to have anywhere between 8 and 16 machines per unit in this box. Right now there are 2, and hopefully really soon it's going to grow in number. In terms of controls, I guess like a general point that I want to make is that all this stuff is hardware that you guys could play with in different forms. We're reusing things that are not, especially for this machine, it's not especially expensive as far as these things go. It's not especially custom or complicated. It's not like we engineered all this from scratch. Most of this is based on 3D printers and CNC machines used for milling. So CNC machines have a very long history. They're used very heavily out in factories, industry for making parts in metal and wood, plastic, all kinds of things. You've probably, I'm sure you're very familiar with 3D printers and how they work. And it's really all the same stuff. It's very similar sets of problems. You're trying to move a tool along a precise path to get some outcome. And generally CNC machines are subtractive. So they've got a spinning bit and they remove material. In our case, it's usually additive, but of a different sort than a 3D printer where you're putting down paint and it's adding up in layers to get the final effect. And then a 3D printer, of course, you're depositing material to build the object that you want. But the underlying control is all pretty much the same. So in this machine in particular, we're using a controller board called the Duet. And that's a really common control system for 3D printers. And it's running the RepRap firmware. So the RepRap project is an open source effort to make software and hardware for 3D printers. And it's been around for a long time. You could go and look it up right now and see a whole bunch of material about kind of the low level control of these systems. It's really handy for us because it's open source and we can make whatever modifications we need for our system. The Duet is great because it's this kind of flexible control board and we can repurpose it for our uses here. And then most of the custom stuff that we do is on the preparation of the job. So if you imagine the output ends up being very similar to a 3D printer in the sense that we're generating a tool path. And then as soon as it's a tool path, the controller knows, oh, this is a tool path like any other tool path. I'm just going to treat it the way I normally would. It doesn't realize that it's not 3D printing something. It's just saying, you're giving me a path to follow. I'll do my best to follow it. And from that point on, it's the same from the control system perspective. But on the input side, we have to make that toolpath in a really special way because the exact nature of it, the speed the tool moves, like which tool it is, the exact shapes of the pads, a lot of small details contribute to the aesthetic effect of the painting. And there's another aspect to it as well that I find really fascinating in general that's related to control theory and so these more general sort of robotics challenges. It's a dynamic problem. When you're working with paint, and liquid, wet things. There's a lot of chaos. You get splatters, sprays, drips. It dries, while you're working, so the effect you get changes. And human painters know how to deal with that intuitively. They spend long time learning a model in their head of how that works, and then they use that to make the marks. They understand, you need to work in layers and put down a particular dark or light, depending on what medium you're working in. You need to let certain layers dry before you can do the next ones. That's all part of the skill that you learn as a painter. And we, with robots in general, you have to teach them everything from scratch always. It's even if you're using more recent advances in machine learning, you still got to have some source of information for them to learn from. So either that's direct experience for the machine. I'm excited about these new machine learning techniques, but it's not yet been applied to this. But more traditionally in classical robotics, you come up with some rule set that explains, for this input, I'm going to generate this output in order to get an effect. And we as engineers come up with that mapping for the machine, and then it gets encoded into hardware and software, and then that implements this mapping to get the effect that we want. But of course, it's code, so you can. It's not just for one painting. You can come up with the system for a set of tools in the machine, and then you can feed in lots of different inputs and get lots of different outputs without repeating all the effort. So I guess I'll show you a little bit, just the machine moving and kind of the basic interface, and then I could jump into the preparation of the toolpath, which I think is that's kind of the more subtle, technically interesting part, maybe. Okay. All right. So I'll share my screen. Let's see. Hopefully this works. Okay. All right. Can you see this web interface? Great. All right. So this is just the baked in web interface that is served by the Duet controller. So the Duet's cool because it's a whole little computer. Mostly, it's an embedded system. It doesn't run Linux or something like that, like a high level non-real-time operating system, but it's running low-level RepRap firmware. But the RepRap firmware is pretty capable. It's running on a 32-bit processor for the Duet board, and can do quite a lot. So it's able to run a web server and send Chrome on my laptop this web page that gives us controls. So let me see. I'll move it around. So you go to the dashboard, and if I just click these buttons, you can see that it's jogging around. Setting up a job, it's a lot of this kind of stuff, just fiddling a little bit. It's hard to get around that and fully automate everything, but there's always a little bit of this. There is some automation, so the system has sensors on board. This is same thing as on a 3D printer. I'll hit the home button, and we can see that each one of the axes move until they hit a little capacitive sensor. So the sensor looks for changes in the electric field, and then it can detect that the piece of metal has gotten near it, sends that to the Duet, and then the Duet says, I know where this part of the machine is. So after it does that for all three, like it just did, it knows, at this moment, it knows it's in the upper left corner. And because of that, the machine is homed. And from this point on, we send commands to the motors that tell them exactly where to move. And we keep track of what we sent to them. And then we're able to know where the machine is, where we're telling it to go. And this kind of control is called open loop. So after we do this homing, we just assume that it's doing what we told it. And we have no way to check. There are no sensors that are kind of live reading the position. if we pushed it and applied some displacement that it doesn't know about, that we didn't tell it to do, then it's lost and everything gets messed up. That's one of the compromises with a cheaper system like this. It would be more expensive to have the sensors that provide closed loop feedback, and it's slightly more complicated to implement. So it's a trade-off. But I guess that gives you the basic idea of like kind of the motion and the control. And then I'll show you how I prepare the job, and then maybe we can jump back to running the job at the end. Okay, cool. All right, so thank you. I'll jump on to a different, now mostly we can just do it on my computer screen. So I wanted to point out that all of this stuff is, for the most part, it's things that you guys could play with right now and make your own art. You could do this whole process. You could make some art, translate it to a toolpath, and then run it on a machine, even a 3D printer. And maybe I'll put, there are a lot of ways you can use those traditional machines in a particular way to output art and get a different result than you normally would. Even if you think about a 3D printer with no modifications, just the deposition of that filament, you could use that to make a picture just on the flat bed of the printer if you wanted to. And that would just be a very particular kind of 3D printing job. So all of this applies to that. We use a whole bunch of tools that are a mix of commercial things but mostly open source, freely available software. So a big one of those is this tool called vpipe. Vpipe is a Python utility that is used to translate SVGs to different formats, different structures. So particularly for pen plotting, where you have a machine very similar to this, or exactly like this, that follows a path holding a pen and makes an image. A really popular one that you can go buy, it's called the AxiDraw. It's a commercial product that comes in different sizes, and you can just put it on your desk. There's some, if you ever want to give that a shot, there's some cheaper ones that are out on Amazon. The real AxiDraw is a little pricey, but the knockoffs are just as good. There's a question?
Not exactly a question, but we at HackCover are building this thing, like modular thing, where we put a kind of a pen plotter. And for an experimentation, we kind of did this, like we strapped pens to a 3D printer and just, so yeah, the drawing thing. It's a ongoing project in Hack Club where we're building a kind of CNC pen plotter machines. Wish Leo would be here though.
That's really cool. Yeah, hopefully I show you guys some new stuff and it's useful. I think it's great that there's a lot of resources out there on the internet to build your own machine and to set it up, but I feel like it's still really spread out. It's kind of hard to gather everything you need. So yeah, hopefully this helps a little bit. Is there another question?
ArtMatr is mostly actually this is my kind of a question, but ArtMatr is mostly focused on the hybrid art. I mean like something that is linked to real life and computer. If this works very well, why not making a robot art galleries?
By robot art gallery, can you explain a little more about what you mean?
Like robots, like you produce text to image prompts, but it's mostly focused on robots. So that will be like a robot automated gallery.
Yeah, are you're particularly interested in like the kind of machine learning approach where the automated translation of say like text to image, but that for these sort of robotic art systems?
Yeah, I am kind of interested in this.
I think that's an exciting area. Like right now, the stuff that we're working on is very, I'd say it's a little experimental, but not very. It's tied to what people in the market want, and then when we have a chance, we're working on more experimental things. And I would classify the machine learning based approaches to art production as that more experimental. There are lots and lots of image based generative systems out there now, and they're really interesting. You know, if you look at the especially like Stable Diffusion is a great relatively simple to understand architecture, and that you can play with on your computer, your laptop, if you've got the model downloaded. If you do that and then you try to apply it to a robotic art system, you'll find really quickly that the challenge is it's image data, it's raster based, or that is to say it's pixels in rows, and what you need out the other end for one of these robotic systems is a toolpath or like a joint trajectory in the more general sense for like another kind of any kind of robotic system. It'll have joints, the various degrees of freedom you have to control. So for a robot arm, it's all the how you would think about a joint, but for a rover on the ground, it would be the wheels and et cetera. The really general version of this problem is like, how do you take a art image that you might want to get at the end, and then generate all of the joint trajectories that you need for the robot to execute that. And if it's a online dynamic problem where, especially if you imagine like a rover that was driving around, and I don't know if you've ever seen Logo, like turtle bots. Yeah, like these sorts of machines. This kind of thing works well. It'll open loop, like it'll work open loop. Okay, if you know how far you've driven and how much you've rotated, then you can make a target image. But if you're in an unconstrained environment, like you're on rough ground, or your machine doesn't have the kind of tight control, then you'd need to kind of close the loop and have feedback and solve the dynamic problem. So anyway, long story short, like there's a lot of work to do to cross that gap, where instead of you generating an image with pixels, you generate that kind of general control data that you need for a robot. I think that's a very exciting thing to work on. I'm particularly really interested in that. And yeah, I have more thoughts. I'd be happy to share another time, but I'd recommend looking into it more. Maybe
Owen.
Yeah.
I would like to use this as a wonderful segue into, we have some pixel art. We did not give you control instructions. Could you kind of talk through your thought process for turning that pixel art into machine control instructions, and maybe show us going through the process to do that?
Yeah, definitely. So for that, I used VPipe, and let me make this a little bigger. Just to remind us. So this was the art that you sent, the more recent version. It is challenging. So I could have maybe should have given some tips about like how the machine works. Like if you don't know the problem space, then it's tricky to know what would be a good fit for the system. And I'll say this is a more challenging kind of image for the machines that we work with because it's got a bunch of colors. Color is in general really hard. It's also pixel based rather than like a path. But in general, when we're working with artists, they will give us anything they've got, and we have just have to adapt. So for me, that this is a good exercise. What I did was first, I have to get some paths somehow. So in Illustrator, and these are just standard, design tools. In Illustrator, you can pull in an image and then do a trace. So that goes in and does a whole bunch of different types of edge detection algorithms on the image and tries to find, the edge of objects. And you can tweak all these different settings, thresholds, and et cetera, get the paths in a different format. So what I did was I told it to respect the colors that you gave, but find edges where it could. And then at the other end, I get all these paths and an SVG. And so the SVG, if you've, I'm sure a bunch of you are familiar with this format, but just to kind of see what's going on in here, it's very much like a web page. It's XML, the format. So it's got those tags. It's a tree structure, and inside it has all the paths from your image. So that conversion that I did resulted in these path elements. Inside the path elements in this D attribute, there's this kind of little command language, which is kind of fun on its own, but it has individual commands like M for move and C for curve to, and a bunch of parameters, all these numbers that you see. Those represent the curves in the image that we were looking at. And if you think about it, like this is already kind of what the machine wants, right? This is instructions for how to draw the image. And if you follow these in order, if you're an SVG renderer, you'll make the picture. So one way to talk about the next step of what we're going to do is we're just going to translate it. We've already kind of got at this point the format we need, and or the semantically, like the meaning of it matches what the machine needs. So we just need to translate the format of it, the syntax, to what the machine expects. And in this case, that's G code. And I'll show you what that looks like in a bit. I bet some of you have seen it because it's what you use for 3D printers. So for that, I use vpipe, and vpipe, you can use it on the command line. There's another tool called vsketch that makes it have a graphical user interface, so it's easier to see what you're doing. Basically, you build these little pipelines where you tell it, I want to read an image. So this traced image that I generated from your art, then maybe I want to show it. It crunches for a sec, and hopefully sometimes a long while. It's written in Python. It's not the fastest thing ever, but now we can see the paths. So it's basically, it's outlined your image. And I'll go into a bit, we'll start here, but I can mention how we can address the colors and et cetera. But as a place to start, here's what we've got. Now this more complicated command that I've built here, this is what I actually use to make the file for the machine. So it does a couple other things. One of them is it reads in this configuration that tells the vpipe pipeline what to do. I'll come back to that in a sec. It reads in the SVG. It scales it to a physical size because the digital image they don't necessarily come with any real size. You have to make a decision. So I picked about 10 centimeters. I know that's a good size. I had to shift it around, which is what the translate step does. And then these other three commands are related to the kind of the way that the machine will execute the job. So we have to simplify the paths because there are a lot of kind of extra points that are there that we don't necessarily care about. They might be like points along a line, and we really only care about the endpoints. So the simplify gets rid of all that. then we merge together paths so that the machine doesn't lift up and then like go right back down to start a new. If two lines are abutted to each other, it'll go down, and by default, it'll say, oh, I'm at the end, I should lift up so I can move. And then it'll immediately see, oh, it's, there's another line where I was, I'll go back down and start that. So this gets rid of that and it'll just smoothly go through. And then the last one is actually surprisingly interesting in general, tied to a very difficult computer science problem. Line sort optimizes the time that the overall job is going to take. Because if you think about it, like you've got all the lines and that represents the image. You could do them in any order, right? Like you'll still end up with generally the same result. But if you do it kind of in a dumb way, where you go and you do one over here and then one at the other side and then back to the other side and et cetera through, it'll take a really long time relative to doing them all kind of in order and filling it in, right? So how do you sort the lines so that you get the optimal time? And this is actually related to this famous computer science problem called the traveling salesman problem. So it's an NP complete problem. It's one of the most famous examples of that. There's no way to compute it, a solution to it efficiently for every version of the problem. VPipe implements an algorithm called 2op, which does a pretty simple kind of trick to speed it up. And it doesn't guarantee that it'll give the best solution, but it does a pretty good job and it's relatively quick. And basically it just goes through and it says for every pair of connected points, let me just swap the output position and see if that's faster. And if it is, I keep it. And if it's not, then I don't. And then you repeat that through all the combinations of the points, and the end you'll get probably a reasonable solution, but not the best. And just as a point of reference, like I've implemented a bunch of different versions of this because sometimes we're doing jobs that can take days on the machine. And so a slightly better solution to this problem, it means a lot of money and time, a lot of material implications. Sometimes it's like related to how many times we need to take the work off the machine. It can have big implications. And out in the world, if you're at a startup doing like delivery of food or optimizing supply chains, this problem comes up over and over again. It's like, how do you, find the best route so that, the right amount of food gets, or goods gets to the right depot, or et cetera. So surprisingly interesting small tidbit right at the end there. But then the last bit is pretty straightforward. It does that translation step. gwrite is a plugin for VPipe that outputs G code, so that the duet can read that, the RepRap firmware interprets it, and the machine executes the job. So this is where that configuration comes back into play. I've made this little plot millimeters configuration, and it says basically for each one of these events, like at the beginning of the document, when we start and end lines and et cetera, use this G code to generate it. So after all that, and if you run this command, we get this out.nc file. This is the G code for the job. So G code's like a terrible from a programming language perspective. It's a very poorly specified format it's kind of just used for historical reasons. It makes working, it causes a lot of challenges because it's poorly specified, but in principle, it's very simple. Each line is a command that tells the machine to do something different. In this case, G21 tells it to use millimeters. G17 says we're in the XY plane. G90 is like we're in absolute positioning mode, how fast to go. And then these are all the points. And then the rest of the file is just all the points that we follow through. So now we're ready to execute. So if we check it, and this is just a website called NC Viewer where you can visualize these files. Now you can see kind of what the machine is going to do when it runs your job. So if I play through it, we can see it, jumps around and makes all these lines. It looks like, I honestly, I was a little bit rushed making this file. We can see that through this visualization that there's an issue that if this was a real, some work for an artist that we're working for, I would make some effort to resolve, that we've got the toolpath divided into all these little lines. We could actually resolve that with a different version of this command. Let's see really quick if I can do that. This merge one. Just drag that into here. And yeah, it looks like it works. So now we have a continuous path for that line. And also, you can tell that it's doing a better job because it's generally staying in the same spot and running through the toolpath. So now, hopefully, we send this to the machine and it'll actually do this for real. So yeah, it looks like we've got a good camera angle on the machine. I'm probably gonna, this is a live demo. I'll say the normal disclaimer that, I'm probably gonna make some mistakes, but that's part of the process. The first one, of course, is that we've got bad home. Okay, so first, I'm just going to run it without taking the cap off the pen to just check that the machine does what we expect. I'm going to tell it, we're at the lower left corner of a piece of paper. It's hard to see on the screen. Now I can just upload that file to the Duet and it'll start running it. So it looks pretty good. I don't know exactly, I didn't memorize what it was going to do, but it looks generally like what it should. So I can pause that, cancel it, send it back to the home so I can take the pen cap off.
I just said here a second.
Yeah, you might want to, yeah, it might be a little risky. Okay. Yeah. Yeah, it looks good.
Is that just like a black Sharpie?
Yeah, actually, here, one sec. One of the reasons it's a little chaotic here because we had a show last week, and this machine was making these bags. So all of these were made on that with those pens. So kind of the cheap Sharpie that we've got a lot of.
That's awesome.
And it looks like I messed up the Z. Fix that. You can see some of the problems that the easy mistakes. So homing the machine, finding the right settings for the tools in general ends up being very difficult. It's something that I'm actively working on. It's kind of one of the more mundane types of problems with systems like this, that there are lots and lots of small details that you can make mistakes on as a human. And slowly we're automating more and more of that. And that, removes the human from the equation, but it's not like a 3D printer or CNC machine where it's relatively the same all the time for the different jobs, or you can make it the same by standardizing the tools. It's going to be different every time because each artist is going to want a different thing. They're going to want to use a different tool or medium or substrate. And so we're constantly adapting. So any automation that we put in has to be really flexible, and then we still have to kind of adapt on the fly. And so in general, the approach that I take is more building tools that let us build those specific solutions more quickly. So it's kind of like a second order approach. In this case, you can see like this is the limitation of the tool system that we've got on this machine right now, where it doesn't know anything about the pen. And I just kind of haphazardly positioned it in the holder before we started the call. So it doesn't know the height, and it doesn't know when it's going to contact the surface. And when I started the job just now, I kind of I moved it down too far. So now we're seeing it's never able to pick it up off the page, even though it's moving up and down. So let me see if I can quickly fix that, and then I'll continue the job. Okay, so now it's working the way that it should work. It was probably hard to see on the video, but picked up the Sharpie enough that it wasn't contacting the page when it was running. So actually I should have, let me just start it slightly off.
I wonder when you're doing like client projects, how often does it just work first time, and how often do you have to fix miscellaneous issues as they pop up?
It's a good question. It never works first time ever. Always fixing miscellaneous issues. And I mean, to give a sense or a flavor of the like what the work's like, but we had the show last week and we were still making the paintings like shortly before the show started, working around the clock, fixing issues and prototyping as we went. And actually, while this is being made, maybe I'll show you for a real job that we did a little while ago, what some of the process looked like. So this is a tool that's a little less accessible than some of the others. It's a commercial tool for visual effects called Houdini. You might be familiar with Blender, which is an open source tool that's pretty similar to what this does. And it's getting closer and closer to the same. You can do a lot of the same things in Blender. But basically, Houdini is great for manipulating geometry. And in this case, we had these SVGs that we needed to translate to paintings. And I built this system to load them into Houdini. They get translated into geometry in a kind of 3D environment. And then they get adapted slowly to what's needed for the machine. So different layers get broken out into different types of geometry. We break out the colors and different kind of sections of the image, the background. And then slowly build up different algorithms for generating shapes that'll be interesting for the physical machine. So let me see if I can grab some of those. So like in this case, just mapping spirals to the image. This is an example of doing the image that you sent in order to get the like some interpretation of the color. There are different ways that we could approach it. One is we could use a different machine that has color, that has there's a machine that we've got. Unfortunately, it's kind of hidden behind a wall right now for that show. But it has a head that is an industrial printer, and Mark might be able to go take a look at that. That's like a hybrid system, so we can have this. That's one of them, and then I think back there. That table. There's a bunch of stuff piled back there, but you can kind of see all the way on the left in the back corner. There's a print head that has a whole bunch of these inkjet print heads that are together on this big tool head, and that moves back and forth like you're familiar with in a printer and at home, and it can apply color. So for this project, that's how we approached it. I'm not sure. Let's see if the videos are still up. Okay, so you can see the tool head that's very much like the one that's doing the art that you sent here. That's going up and down with a tool that's a scribe. It's dragging through paint on the canvas and making that hash pattern. And that hash pattern was generated inside of Houdini based on the SVG that was sent. I think that's this. And all the color, we can do with the printer. So this head on the left, you can see there are different ink cartridges, and at the bottom is the inkjet system, and then there's sort of this parasitic tool head on the other side. They both ride the same belt, and we have the little catch that's able to disengage the parasitic head and then let the printer do its thing, and then we can switch back and go back and forth between the two to get the effect that we want. See if that loaded up. So so you can see this is the actual geometry for that job. There are these little hash marks that get built up, and I do instead of using vpipe for this one, I have a custom pipeline that I built in Python that runs inside of Houdini to get this geometry formatted for the machine, because sometimes the exact path, speed, and the behavior of the tool matters for the effect on the output, and vpipe doesn't necessarily have the right commands to invoke in that command line interface. So you kind of that's where you really have to like hack around the limitations of each individual tool and switch back and forth between a lot of different things to get the effect that you want. But I don't know how much time I'm supposed to have, so maybe I'll pause there.
That's really cool. I've only ever seen Houdini as like the crazy software VFX artists use, and it's really interesting to see it being used for like this kind of stuff. For time, we could, it's partially up to you. It would be awesome if we could go until like 12:15 or something. I know Peter earlier in the chat might not still be here, but he was asking oh, you are.
Yeah,
hi.
I am. Hi. Yeah. So
Yeah.
I saw the gallery you had outside. I was just wondering, what was like the coolest project that you personally have seen that your clients have like sent to you guys?
Unfortunately, or the one that I would give is one that I can't yet talk about, but the one that's let's see. I guess I might actually have a video of Well, I'll give a fun one. I don't know if I would say it's the favorite, but it was very interesting to work on. And this is a project that Jeff, who I did wanted to give you, because he wasn't able to join the call, I wanted to give you a sense of what Jeff's done. I think he has a whole different kind of approach than I just described. He's also doing machine art. He's doing he's doing a huge amount of work here on the paintings that are, I mean, really everything going on relative to the production of the works here. And Jeff and I have worked outside of ArtMatr on all sorts of different projects doing same kinds of things. Jeff's been a painter for decades, like 40 years, and taught himself engineering in the last about 10 years to build painting machines for himself. So Jeff and I started collaborating on different stuff and just like working, and we shared a studio for a while. And one of the projects was out of the blue, Jeff got contacted over Instagram by somebody representing this YouTuber, Rudy Mancuso, and they had a kind of crazy project they wanted to do. They wanted to make a machine to translate music composed by Rudy to paintings. And the fun part of it was that they needed it really, really fast, like 2 weeks. And we're in New York City. They're located in LA. So it needed to not only be built, everything figured out, created in 2 weeks, but we also had to get it over to LA and set up and do a full shoot for this production within that time. And I was working a full-time job that was different. Jeff had his own contract jobs and other things going on. So it was a really insane timeline and difficult project, but that made it pretty fun and interesting. If you want, you can go watch this whole video online, but I'll just show you a couple excerpts. Only one section was the machine that we built, which was a version of the machine that Jeff had set up in his studio for his work. So you can kind of see it on the right there, up in the corner. And basically, like we came up with the system. Like I figured out none of the tools we had were fast enough for music. Like this was another aspect that made it a very interesting project. How do you translate music to painting? Like we didn't have enough time to go back and forth with them and kind of brainstorm together. We really had to just make it up as we went because we had no time. So really quickly we realized from the music they started sending over, which actually, let me see if I can. So you can hear there are lots of small notes there, and they wanted them all to show up in the painting. And none of the tools that we had were fast enough to do that. They all have to move through space. They're on screws that take time to turn. No way to keep up. So what I did was set up an air system and a whole bunch of solenoids. And then the solenoids would fire the paint out the head of the machine. You can kind of see, here that there are a bunch of reservoirs. The reservoirs get pressurized at the top, and then that pushes paint through out the needles and onto the canvas. And that was able to keep up. And then I wrote some really janky software to take MIDI, which is a way to encode music into notes over time, and then translate that to commands for the machine. And then that was wired into the stuff that Rudy was using on set. And we were able to do it, but very, very difficult. The tools that you see in this picture here didn't exist. Like that version didn't exist until about 3 a.m. the morning of the shoot. And we had like a all call at 9 a.m. And so very close to not happening at all, but it worked out. So I guess that also gives the general sense is that every project is very different. We end up doing a lot of crazy a lot of crazy things that we're never going to repeat. They're unique to each situation.
That's really fun.
Maybe let me really quickly, I'll give you, feel free to, or I recommend checking out Jeff's work. He has a really great Instagram where he shows a bunch of the machines that he built, but the way that he works is very interesting. We have kind of opposite approaches, and I learn a ton from Jeff every time I work with him on something, because I end up coming from like a analytical, like I want to kind of solve the problem in general and have something that's robust to like every situation. And then usually that means I'm overthinking it and it's more complicated than it needs to be. And often I'm solving problems with software rather than hardware. Jeff's like the opposite. Like he'll solve like the short path with hardware. He'll usually like solve it by picking like just the exact right piece out of some junk bin somewhere and like bending it into the right shape to make work on the machine. It's incredible. Like he builds, like a lot of his machines are built from stuff that he just like saw on the side of the road and was like, oh, that's like the perfect shape. And then he just like picked it up and put it in his car, and it ends up in the tools. He's an abstract painter, so like pretty much all of his work is abstract. He's built like lots and lots of different machines. So here's one. This main machine is the one that's similar to what we brought to LA. That's Jeff. Some of them are kind of, all of these are kind of performance pieces. If you think about it, like it is fun to watch the machines work. So this one that Jeff built is like it puts water onto a paper that changes color when it's wet. So it can keep going indefinitely. It'll dry out and disappear, and then new marks can be made. So it can just run all day. And then the other main part of Jeff's practice with these machines is he'll just make lots and lots and lots of different tools. So I think in the last project we did, he made a couple dozen tools in less than 2 weeks. We just churned through trying different things, showing them to the artists, and then adapting them, trying to make them more robust or get a different effect. That makes it really fun, but it's also hard to, you have to balance, like, do you try something risky that might give a better effect? Or do you need reliability? Because when the timeline is really short, you might find that you're working on the actual final artwork, but you're doing it with something you've never tried. It's like you're testing in production. You have only one shot and it needs to work. So you need to get a sense of balancing risk. And that's good. That's a good general, if you end up doing prototyping, like engineering work where you have those short timelines, you're building anything, that's a general skill that's worth picking up.
That's so lovely, Owen. Thank you so much again for coming and talking to us and showing us all of your tools and your projects and doing this art with us. I've learned a lot from this, and it's been so cool. And you've explained everything in great detail, which I'm really grateful for. But again, we are a group of high school coders and innovators from all around the world, and we're called Hack Club. So we were wondering if you had any questions you'd like to ask us from your side.
Yeah, I'm really curious what you guys are working on or interested in. Like, even if it was just a few words, maybe you want to go around and say like a topic, because I imagine it's all very different.
Oh my God, yes, we have so many ships and stuff. Does everyone want to let's go in a line or something and just talk about?
I think we should start talking about so we're launching a game next month. It's called Steinwriter. I think a lot of people here have worked on this extensively over the past few years. Does anyone want to just summarize what it's about?
I think Eileen would be great. Eileen, aren't you currently working on it?
Yeah, so SignWriter is like an open source game. So any like hack clever that wants to contribute can like work on like an issue and commit to it. And it's about a math game. Like so yeah, it's like it has a storyline about like two ghosts. But it's really awesome. We'll like people are like beta testing it already, and yeah. Yeah, I'll send in a link where you can try it out. It's really fun.
Yeah, I was just looking at some links in chat. It looks really cool. I'll give it a closer look later, but that's cool. So that's like a collaborative project between a whole bunch of members of the club. That's great. Is that I guess another kind of maybe just talking in aggregate about all the different interests, like another question is it mostly software? Are there any hardware projects that go on? I remember there was that plotter that you guys are building, but is that kind of a I guess, and also related, you're all spread out, right? Are there spaces or ways that places that you could go to get resources or local maker spaces or something like that? Maybe Thomas, you've got your hand raised.
Yeah, so Hack Club is a network of clubs. I mean, it's also an online community. So on the online community, the Slack community, we have thousands of high school makers there, but also within the Hack Club community, people start clubs at their own school. So like many people within this call started a club at their school that has maybe 20 members or so, right? I started one at my school, and then every week we meet and build projects together in our individual clubs. And then we also have these larger community projects like the one that was mentioned with the drawing machine. Like another project is Sprig, which is an open source project of building like a game console where anyone can make their own game and then receive a console shipped through the mail. And then there are also hackathons, which are big events where people can get together from all sorts of clubs, all around the world and build projects together in a short period of time.
Really cool.
Yeah, and most of us build software projects just because it's like the most accessible, and we like most people on this call, I think, are probably in like different states and cities as well. So we don't really like come together to work on a physical project, but most of our like projects are all open source. So we regularly contribute to like each other's projects, and like most of it is like individual. We do have a few joint projects that are like the drawing machine that are like led by an engineer at Club HQ, and that's like the nonprofit itself. And so those are like full-timed, and we have like physical stuff, and we have like funding to like build those projects, but lots of people build on their own like small projects as well. Although we did recently have a grant which went out for $250 for people to build their own like hardware projects, and we had people build like snack machines, like piano playing robots, like just different small things with their friends in their local community too.
It's definitely kind of hard to do hardware, like at least collaborative hardware projects with like the decentralized nature of Hack Club. And also there's kind of a cost barrier for all hardware stuff. So I think people tend to gravitate towards working on software projects just because it's so accessible to everyone and easy to collaborate on online. But there's definitely, I think, an increasing interest in hardware stuff over time, which is super cool to see.
Yeah, I remember. I wish there was something like Hack Club when I was growing up. I was out in like a rural place, and yeah, getting access to hardware to play with was almost impossible. So I just took apart junk, and yeah, you have to make do with whatever you've got at hand. But that's really cool. I'm glad. It's incredible that you guys are collaborating on these big projects together. I think that's really encouraging. But I guess like maybe in the vein of after this, like I'm very happy to share anything that would be useful for really any project that you guys are working on. You know, we don't have any, this is very much a startup. So it's like kind of, we're always short on time, money, and it's always chaotic. So we don't really have a plan in place yet for open sourcing like the tools that we're building or using, or kind of explaining what we're doing. But it's very, I'm very willing to share that directly. Or if you have like particular requests or want elaboration, or you saw something that might be useful for something that you're working on, I can definitely share that. I don't think there's any, and I'd be happy to explain and help as I can.
That's an amazing offer. Thank you so much. And thanks for being here and showing us all of the cool shit you've been doing. This has been really, really fucking interesting.
I'm glad. Yeah, very much my pleasure. Cool.
Excellent. I think we should wrap it up.
Good place to end. All right. Yeah. Thanks for listening.
Thank you so much for coming and
Yeah,
spending an
thank
hour.
you.
Thank you so much.
Thank you.
You're welcome. Goodbye.
Bye.
Bye.